Let's talk about vector equations. Specifically, we'll be looking at vector arithmetic. First off, let's define what we mean by vector. A vector is really just a matrix that is either one column or just one row. So an m by 1 or a 1 by n matrix is called a vector. If it's just a column, we call it a column vector. If it's just a single row, we call it a row vector. So for example, here's a few column vectors. 1, 2, 3 would be a 3 by 1 column vector. I could have a longer one. Here I have a vector of 5 ones, which is a 5 by 1 column vector. We could also have some row vectors, so for example 1, 2, 3, 4 would be a 1 by 4 row vector. I could also have a smaller one if I had 0, 1. That would be a 1 by 2 row vector. We say two vectors are equal if and only if their corresponding entries are equal. So very simply, the vector 1, 2, 3 is equal to the vector 1, 2, 3 because these vectors are the same size and they have the same entries in the same locations. 1, 2, 3 does not equal the vector 1, 2, 0 because in the last place, in the first vector, we have a 3 and in the second vector we have a 0. Similarly, the vectors have to be the same size in order to be equal to each other. So the vector 1, 2, 3 as a column is not equal to the vector 1, 2, 3 as a row. Now let's talk about some arithmetic with vectors. We can add two vectors together provided they're the same size. We would add the corresponding entries. So for example, if I had the column vector x1, x2 on up to xn, I could add that to the column vector y1, y2 on up to yn, provided they're the same size. And in order to add these two vectors together, I would just add the corresponding entries. So I would get x1 plus y1 in my first entry, x2 plus y2 for my second entry, and similarly xn plus yn for the last entry. Scalar multiplication is even easier. If I want to take a scalar number c and multiply it by a vector, say my x1, x2 through xn, I simply multiply that scalar times every single entry. So my resulting vector would be cx1, cx2 on up to cxn. To easily see how we can use scalar multiplication and vector addition together, let's look at the following example. Here I have vectors u and v, and I'm asked to find 3u minus v. So first off, I will calculate 3u. That would just be 3 times every entry of u. So I have 3 times 1, 3 times 0, and 3 times 3, which gives me the vector 3, 0, 9. And now I'm asked to find 3u minus v. So I'm going to take that vector 3u, which I just computed, and now I'm going to subtract off my vector v, 2, 1, negative 1. And at this point you might be concerned, I only taught you addition and didn't teach you subtraction. Well, subtraction works the same way addition does, you just do it entry-wise. So in this case, I'm going to subtract 3 minus 2, take corresponding entries, 0 minus 1, and 9 minus a minus 1. And if you do that computation, you get 1, negative 1, 10. You might wonder, what is the meaning of this idea of vector addition? Vector addition in 2D can be easily visualized. So if I want to add vectors u and v together, the way that looks in the plane, if u and v are in R2, would be we could visualize u and v pointing to 2 points in the plane, and their sum, u plus v, points to yet another point in the plane. And that is the point that's formed by making a parallelogram with sides formed by the vectors u and v. In 3 dimensions, this has similar meaning, except we're looking at a parallelepiped. Finally, let's conclude by looking at some of the algebraic properties of Rn. So suppose we have vectors u, v, and w in Rn, and we have some scalar numbers a and b. Then we get the following list of algebraic properties. Many of these should seem very familiar to you if you've taken a standard algebra class. So for example, a plus v equals v plus u. That's the idea of commutativity. U plus V plus W can be reordered in an associative way so that you can add first U plus V, or you can add V plus U first and then add U. There's an additive identity and an additive inverse. And when we start to look at moving the scalar in there as well, the scalar is distributive over vector sums. We have distributivity over scalar sums. We have associativity of scalar sums. And finally, 1, as you might expect, is our multiplicative identity. Later in this course, we'll look at what it means to multiply two vectors together. And it doesn't mean what you think. Unlike addition and subtraction, which we did entry-wise, we won't be looking at multiplication in that way because it won't have the properties that we want our multiplication to have. And that concludes this lecture on vector arithmetic.